Okay, dear students, today I am going to discuss a new topic in this chapter, that is diffraction of light. So, diffraction of light means it is the bending of the light around the edges of the corners, sharp corners or slit, and it's spreading into the expected geometrical shadow region. So, this phenomenon is called as diffraction of light. So, whenever light passes through the narrow edge or a slit, it undergoes bending at the edges and it spreads into a region where we expect a shadow. It spreads into the region where we expect a shadow. Actually, there should be shadow, but dark region. But we don't get that dark region, but because of the light spreads into that region after bending at the edges, so some intensity of light is observed. So this bending of light at the small edges, thin edges, sharp corners like a razor blade, a tip of the needle, all that. So that phenomenon is called as diffraction of light. So diffraction is the phenomenon which is observed in all types of waves, not only light. Sound also undergoes diffraction, matter waves, water waves, ripples on the, so everything, all the waves, whatever waves are there, they undergo the property or the phenomena called as diffraction. Bending will take place in all types of waves. Okay, so matter waves diffraction is used in the de Broglie's hypothesis. It is explained, and it is used in the construction of microscopes. Okay, so that is what the application of this use of matter waves in the field of microscopes. Okay, ultra microscopes and electron microscopes. Particularly, it is electron microscopes where we use the wave properties or diffraction phenomena of particles is taken into account. So, diffraction of light, there are mainly two types of diffraction: Fraunhofer diffraction and Fresnel diffraction. But in our discussion as given in the NCERT book, only we restrict ourselves to Fraunhofer diffraction. That is the source is at far distance and the screen is also at a far distance. And examples for diffraction of light, there are some examples like the CD, compact disc. Earlier we are using, nowadays it is very rare. So that CD, when you expose into light, white light, sunlight or white light, it shows different colors. So that is because of the diffraction phenomenon. Okay, so the next, the spider's web exhibits different colors, spider's web. So that is also because of the diffraction of light. Okay, so the diffraction is the phenomenon of light, bending of light takes place. I will give one example. Suppose there is a source of light, a point source, and if I keep a narrow hole here, okay, narrow hole here, I keep on a surface, I keep a narrow hole, small hole. Now you expect that light will go like this. Okay, light will go like this, and if there is a screen like this, and we have here some bright region at this. Here we have some bright region. That's what our expectation. But because of the diffraction phenomenon, at the edges of this, that light will spread into geometrical shadow, expected shadow. So here is this much region, not a line actually, it is a circular region. So this much region is exposed with light, but actually light directly cannot come there, but bending of the light at the narrow edges or sharp corners takes place and it spreads into the expected geometrical shadow here. Expected geometrical shadow, here also expected. So only through this opening light process we get here intensity of light, but here also some intensity of light is observed. That is because of the diffraction taking place at the edges. This is one example. Similarly, another reverse example I can give. Suppose if I keep the source here, same way another situation I create. If I have some obstacle like a coin, okay, so this is the opaque body. So the light goes like this, okay, so light goes this way, and here also it goes, and if I place a screen like this here, okay, so then we expect light here, this side light is there, here also light is there, but because of the diffraction diffraction phenomenon, the light spreads into this region. Here also some intensity will be there. Here also some intensity will be there. So that means some intensity of light is observed beyond the expected region. Okay, where we expect a shadow here and here, there is some shadow supposed to be. But because of the diffraction at this edges, so light will spread into the dark region. Where we expect a dark region, that becomes partially bright. So there will be some light intensity. So light bends at the edges or corners. Not only light, diffraction is the basic property involved in all types of waves. Okay, then we will go to the study the diffraction. That is diffraction at a single slit. Diffraction at single slit. So in interference we have studied some experiments like Young's experiments, all that. Here also diffraction at single slit we study. Single slit. Okay, so here there is a slit. Slit means a narrow opening like this. Okay, it is very narrow actually. The size of the slit may be millimeter or less than that, or around 1 millimeter or 2 millimeter like that, or less than that. Okay, so width of the slit. So this point I will take it as L. Okay, so here I will take this one. Okay, width also I will take for this. So here is L, M. Okay, N I will take. Now I illuminate this slit with white light. Okay, I illuminate this slit with the monochromatic light. Monochromatic light. Monochromatic light. Now what happens on the screen? So screen you may expect, okay, you may expect only this much will be the bright region, correct? So light passes and only expect this much region will be bright. But okay, so this we have central maxima, and not only this much, there are secondary maxima and minima. Secondary maxima also observed. So some point here also some intensity is there, some point here also some intensity is there. Again dark will be there, again bright region. That means we don't get only this region is with some light intensity, but we get other regions also. Beside that, central maximum or principal maximum will get alternate bright and dark regions called as diffraction bands. So the study of this, what we do, so the screen is placed at far distance. Screen is placed at far distance. In this case, that is actually Fraunhofer diffraction. So this light travels, okay, and it goes to the center of the screen. Okay, so this direction I will take as center of the screen. Okay, so to C. C means this is the center of the screen, and screen is placed at far distance. And the light undergoes diffraction. So that also you have to show here. Okay, so light undergoes diffraction. So here it goes this way. And diffracted light goes to various points on the screen. Okay, so this is to point P. Okay, point P may be bright or dark region. So it depends upon the path length conditions. Okay, this is to go to reach the point P on the screen. Okay, so this angle is called diffraction angle, angle of diffraction. It is same here, angle of diffraction. Then the path difference between the light traveling from L, this point, and path difference between the light traveling from this point. So that path difference is there. No? So that path difference we have to study. So that path difference is, so from light travels from here, and somewhere middle I will take as M, okay, and the light traveling from this edge, the distance traveled to point P is NP, and from this point the light travels a distance LP. So the path difference in the diagram, path difference between the light traveling from N as well as L, so that difference is, okay, so the difference is NP minus LP. NP minus LP. So that is the path difference. That is equal to A sin theta. Okay. So that difference is equal to A sin theta. where theta is the diffraction angle or the angle made by this direction of light with respect to the normal to the plane of the slits. Okay, plane of the slit. So a sin theta. For a small angle, sometimes we take sin theta as nearly equal to theta, where theta is expressed in radians. Okay. So path difference. So from here to point P, NP is the distance. It is more distance, and from this edge of the object, LP is the distance. So NP minus LP. NP minus LP is the path difference. So that is the path difference. Now we have conditions for bright fringe to observe or bright region to observe on the screen at a point P. Okay, so that is called as diffraction maxima, secondary maxima. So condition for secondary maxima and minima are like this. Okay, so firstly, condition for secondary maxima. Condition for secondary maxima. Secondary maxima on the screen. Okay, so that is a sin theta equal to So in case of interference, path difference equal to n lambda is the condition for bright region or the maximum intensity region. But here path difference is n plus half lambda gives you the bright region at the point P. If this path difference NP minus LP or a sin theta is equal to n plus half lambda, where lambda is the wavelength of the light used in the or illuminating the slit. Okay, so this is the condition where n equal to 1, you can take plus or minus 1, plus or minus 2, etc., plus or minus 3, etc. So with this condition we get a bright region at the point P. Okay. So similarly, we write the condition for minimum. Condition for minima in diffraction. Minimum is many are there. Here when you take n different values of n, you will get different values. Okay, different values of theta will get and okay, different. It is applied to different maximum and minimum. So now minima condition. Okay, so the path difference. This also path difference only. Path difference only it is. Path difference is sin theta, n plus half lambda for maxima, secondary maxima, whereas path difference a sin theta equal to n lambda. These were the conditions for maxima in interference. A sin theta equal to n lambda is the condition for maxima in interference, but here it is the condition for minima. So a sin theta equal to n lambda is the condition for minima, because many values are there here. N value you can take plus or minus 1, plus or minus 2, plus or minus 3, etc. With these conditions we get a bright fringe, a dark fringe on the screen. That is here dark fringe means a dark band, diffraction minimum. So here dark region is not perfectly dark, unlike in case of interference. In case of interference, if you use two light sources illuminating the slit, so S1 and S2 giving the light intensity I0 and I0, the dark fringe will be perfectly dark, whereas here in diffraction the dark fringe is not perfectly dark. Some intensity of light will be there. So these are two important things in this part, that is conditions for secondary maxima and condition for minima in case of diffraction. So path difference a sin theta n plus half into lambda. Okay, where n value we have to write, compulsorily you have to write n value, and also you have to write what is lambda. Lambda is what? Lambda is the wavelength of light. Wavelength of light. Lambda is the wavelength of light. Compulsorily you have to explain the terms. Question will be mention the conditions for path difference in diffraction for maxima and minima. Okay, so wavelength of light is a lambda symbol. Wavelength of light. So that's all about this theory part of this diffraction single slit. Now the intensity distribution curve. So what do we get? How the intensity distributed on the screen? Okay, so whenever a single slit, narrow slit, the width of the slit may be millimeter or less, or around 1 millimeter, I can say 2 millimeter, etc. Not very large, small region. So then diffraction maxima and minima are observed on the screen placed at a large distance. The intensity distribution curve. Okay, so I hope you understood this part. So I will show the intensity distribution here itself. So this is the slit here. Okay, so this is the slit. Light incident or falls after diffraction. Okay, on the screen. So if I show the screen, so this is the region where we get the bright region or principal maximum. So what exactly happens in case of diffraction? In interference we have seen the light coming from two different slits superpose each other and produce a darker bright region depending upon the path difference or phase difference. Whereas in diffraction phenomenon, this you have to note down, where in diffraction phenomena, light from various part of a single slit, so upper part here, lower part, middle part, all that, so light from different wavefronts emitted from the different regions. Okay, so wavefront is there here, the superposition of the light waves coming from the different regions of a single wavefront here, only one wavefront is there. So from different portions, different parts of the wavefront superpose and give dark or bright region on the screen. Okay, so that is the light coming from a single wavefront or single slit itself. From various parts they superpose and gives rise to maxima or minima. So intensity here, so this is the point C here. Okay, C. There will be bright region, I said. Intensity will be large. Okay, then maxima will be having less intensity. Okay, so this way I have shown. That means at the center of the screen, highest intensity. This raised portion shows that maximum intensity. Then intensity decreases. So here, somewhere here at this point on the screen, almost 0, not 0. So intensity very less here. That is called as minimum. Then again secondary maximum. This is the first secondary maxima here and here. Okay, so intensity increases. Actually, if you take like a small hole, then you may not observe this maximum minimum. But because it is the very small slit, very small slit means millimeter width. So then we observe like this maxima and minima placed at a large distance on the screen. Yes. Okay, so then next this graph, intensity distribution graph, I am going to draw in the way like yesterday I discussed the intensity distribution curve in interference. So this is the graph. So intensity along y-axis, intensity on the screen, okay, along y-axis, and here along x-axis is the distance. Okay, x-axis distance is there. So bright region is formed on the screen at the like this. Okay, like this. Okay, so then the secondary maxima what we get, those will have lesser intensity. Okay, so this is the point C, that is center of the screen, having highest intensity. This region is the highest intensity. This is called as principal maximum. Intensity is maximum for central maximum, that is a principal maximum or central maximum. Central maximum, highest intensity, the center of the screen, because it is directly opposite to the slit or the hole. Okay, now these are all secondary maximum. This is the first secondary maximum. I have show and label that in the graph. Okay, first secondary maximum, and this is the second secondary maximum. Second secondary maximum. Okay, so then here is the first minimum. First minimum at this point, and here is the second minimum. Second minimum, and the same thing we observe on the other side also. Okay, so this is the first minimum, This is the second minimum. Lower part in the graph, it is intensity curve. Y-axis intensity is there. So more highest intensity at this point. Center of the central maximum is having highest intensity. And as you go away from the center of the central maximum on the screen, intensity gradually decreases on either side. Intensity decreases and becomes a minimum value. It may not be zero value. Minimum value it becomes. Okay. So then that region on either side of the screen we call it as a first minimum. And then again after it becomes minimum, again intensity gradually raises to a certain value, but not that much as central maximum. The intensity of the secondary maxima is lesser. It is less than the central maximum intensity. So intensity gradually decreases. Okay, so then it becomes 0. Then again it becomes very small. Then increases, becomes maximum. Again it decreases minimum. Then like that. So alternate dark and bright regions are observed. Alternate dark and bright regions are observed on the screen. They are all secondary maximum, central maximum or principal maximum, first minimum either side. Okay, so that's what the intensity distribution curve in the case of diffraction. In case of interference, in the previous session I have discussed, all the intensities are same. Intensity of central bright fringe, first bright fringe, second bright fringe, third bright fringe, like that, all are at same height. Means what? Intensity is the same in case of all the fringes in case of interference phenomenon in double slit. Whereas here it is intensity is decreasing as you go to the higher order diffraction pattern. So the intensity decreases. Intensity decreases in the case of secondary maxima, and more order if you take, then intensity will be less and less. That's all. That's all about the graph. Now the basic distinction between the interference and diffraction. So when it comes to differences or distinction, okay, differences between interference and diffraction. So we have to make two columns and list out the differences instead of writing continuously. So better way of writing the differences or distinction or distinguishing between the two phenomena here. So interference and diffraction, it is regarding light, it is not other phenomena generally. So it is interference of light, diffraction of light. So what are the basic differences between interference and diffraction? So the definition we can write. So interference is the modification in the distribution of light energy due to the superposition of two or more light waves. That is the interference. Whereas the diffraction definition, it is the bending of light at the edges of sharp corners or narrow slits, and it's spreading into the expected geometrical shadow region. So that is diffraction. Next, in interference, the light coming from two different coherent sources superpose, or two slits we can say. The two slits act like two coherent sources in Young's double slit experiment. So light coming from two different sources, different slits, coherent sources, will superpose, produce alternate dark and bright regions on the screen. Whereas in diffraction, second point is light coming from different parts of same wavefront, same slit, from the different parts of same wavefront superposes on the screen and producing dark and bright regions. Then intensity of all the bright fringes in interference is the same. But here intensity is not same or unequal. Intensity of the bright fringes is unequal, or the intensity of the secondary maxima decreases as the order increases. Then width of the fringes. In interference, the width of all the fringes will be equal. All the fringes have equal width, whereas in diffraction, fringes have different width. Width of central maximum is different, width of the first secondary maximum is different, secondary maximum is different. So width is unequal. Okay. Then conditions for maxima and minima you can write. So here maxima condition in interference. Okay, path reference A sin theta equal to n lambda, whereas here A sin theta maxima condition in diffraction is like this. A sin theta equal to n plus half lambda. N plus half lambda, but mention that values n is 0 plus or minus 1 plus or minus 2 etc. here also, and mention lambda is the wavelength. Okay, so there is a 1 here, it starts from plus or minus 1 plus or minus 2 plus or minus 3 etc. Maxima condition in diffraction, maxima condition in interference, here n lambda. Now in minima it is just reverse. So here minima condition is in interference, minima condition path reference. So make sure that A means here distance between the slits. Actually we use the small d. For distance between the slits we use the symbol small d. But for comparing I want here same, that's why you can take d also here, where d is the or A is the distance between the two slits S1 and S2. Here A is the width of the slit, that how much width that slit is. Okay, so here A is the, so A sin theta, path reference A sin theta equal to n plus half lambda is the condition for minima in interference, whereas here A sin theta equal to, okay, n lambda is the condition for minima in case of diffraction. Okay, then next after that we have one more important differences, that is we can write is contrast. The contrast between dark and bright fringes in interference is very good. There is a good contrast between interference and bright and dark fringes in the interference. Now how you understand the contrast part? See, this is the bright region. Okay, this is the bright region and there is a dark region. Okay, then dark, bright, like this, alternate, equal width actually. Okay, equal width will be there between dark and bright fringes. All the bright fringes have equal width, all the dark fringes have equal width. So like that. Now you see clearly there is a dark region, there is a bright region, dark region, bright region. But in diffraction what happens? See, the center of the maximum is highest intensity. The intensity gradually decreases. Okay, gradually decreases and fades to very least intensity. Okay, on either side. Okay, again there is a secondary maximum. So now what happens, you see here. So the bright region is there, but gradually fades. So where the dark fringe, where is the bright fringe, is difficult to understand. That's what poor contrast. Here we can say clearly where is dark. This is the dark region, this is the bright region, dark. So this is very good contrast. Here poor contrast. The contrast between bright and dark fringes in interference is good, whereas the contrast between bright and dark fringe regions or bands, diffraction bands, is poor contrast. Here good contrast. So that are the major differences between interference and diffraction. So these conditions are very useful and they ask in the exams differences between or the distinction, or write the conditions for the bright fringes or dark fringes in interference, also same way in diffraction. Write the conditions for dark and bright fringes, bright regions or bands, or they can ask a maxima. Write the condition for path difference in diffraction, for maxima and also for minima. So those questions can be asked here. That's all about this diffraction phenomena. One is intensity distribution curve. Okay, so that's all about this topic. In the next class I will discuss the next problems, or if possible I will discuss the resolving power, and in the new syllabus it has been cut down, that topics are reduced and it is deleted.